Here in section 11.3, we introduce a velocity controller. We're going to look at the weaknesses of the position controller and then introduce the velocity controller example and finally present some challenges in analyzing the response. When it comes to position control, we saw that higher loop gains can lead to better tracking performance. However, if the gains are too high, we're going to have more instability. The question now is, if we also begin to change the set point quickly, how can we have good stable tracking performance? The idea is that we can take, in addition to a position loop, a velocity loop with some feed-forward terms. The velocity loop right here can have a velocity feed-forward term coming from a loop like this. The velocity can be computed directly as a derivative of the position and multiplied by a gain. How does this help? If the position profile changes quickly, or if the current position of the robot changes quickly, then this feed-forward term will notice that change very fast and adjust for the change in position or velocity. The fact of using a velocity feed-forward term will help our response to be 2 times or more better. However, some shortcomings are that the feed-forward term for the velocity can induce an overshoot, but this can also be limited by including an additional acceleration feed-forward term. So in ROS, we could use these concepts by running a velocity controller and then add the external position controller and feed-forward terms. Yep. So the feed-forward terms and the position controller just are the input to the velocity controller. However, for simplicity in this section, we're just going to limit ourselves to introducing the velocity controller and its analysis. As before, let's look at the launch file for the velocity controller. And you'll notice that the main change here is that in controller manager package spawner node, we have a different name for the controller, joint 1 velocity controller. We also note that we will set the starting joint angle for joint 1 to be at negative 0.5 radians, which is the mid-range position of the joint. In the configuration file for the velocity parameters, we see that we have our joint 1 velocity controller as the name, and the type is now joint velocity controller instead of joint position controller, and we have some changes in our PID gain values. And finally, since we want to test dynamic set points, we want to run a sign commander node. Yep. Actually, let me click on that. This sign commander node, actually I have it right here, is basically going to be publishing to the command topics for the velocity controller and the position controller. So this is going to help us to provide the set point for our velocity controller. So we will start Gazebo as usual and then run the joint velocity controller launch file. Start RQT-plot to look at the commanded data, the velocity, and the efforts. Finally, we run the example controller's 1 degree of freedom sign commander to provide the set point information. When we do this, the last node will request for user amplitude and frequency, which we can set to 0.1 as a small response, and then a frequency of 3 hertz. That'll be 20 radians. Now, over time, you'll see that the amplitude will drift away from the 0.5 with amplitude of 0.1 range, and it will lead to some collisions. In general, we see that this controller will have better initial tracking than the position controller. Our red curve will very closely track our commanded curve in this way. The tracking can be improved by adjusting the proportional, the derivative, and the integral gains as well. And In this case, we don't have a sine function that is changing its frequency at different velocity rates. It usually has a constant rate, so it's a somewhat simpler tracking problem. But we do face some challenges, as you'll see, and one is that the dynamic response, it's challenging because the second link can drift from the center and sometimes hit joint limits. When there's collisions due to joint limits, we introduce distortions into our system. And collisions of this kind may also be triggered when gains are changed. Some things we can do to diminish reaching those limit locations is, number one, to set the gravity in gazebo to 0. This will allow joint 2 not collapse under its own weight. So that's a good thing. Starting joint 1 in the middle of the range, as we did in our launch file, will also diminish collisions. And this in turn gives us more time to evaluate the dynamic response of the system. Finally, you can consider including, as we mentioned before, an outer position control loop to correct for drift from the velocity control closed loop. And then including the feed-forward terms for velocity and acceleration. This concludes section 11.3 with the velocity controller, and now we will study force control.